Okay, thank you so much for the nice introduction. And yes, absolutely, the cut and paste invariants of manifolds was a topic that was very important in the 70s, and this group of at the time young authors, Karras, Craig, Norman, and Osa, have this beautiful book on cut and paste invariants and how they formalized it as groups. So so it's very interesting how you have these groups of manifolds according to a certain relation, and how you also have cobordism. And how do those two things relate? Well, that's an interesting question. It's also interesting how there's various different ways on how to approach and how to formalize cut and paste invariants. So I'm going to review the classical theory today as well. But I'm also going to present some generalizations and some other points of view that I worked on with a team of collaborators, Renee Hoekzema, Mona Merling, Laura Murray, and Julia Semikina. So this talk is based on two different projects. The first of them was born as a project for Women in Topology 3 a few years ago, and I will talk about those results. And then that team of authors, we continued working on different aspects of the project, not exactly the same team, but I continued working with Renee and Julia. Of course, COVID did hurt us a little bit because we were separated in different continents. We weren't able to get together. And somehow people who were in Europe continued working, people who were in the US continued working. And then in the end, it's been a very nice continuations in different aspects of this story. Okay, so before I actually start with the actual manifolds and cut and paste invariant of manifolds, let me give a little bit of motivation of what we mean by cutting and pasting. So the most classical version of the problem in cutting and pasting is you could think about polygons. So it would be like cutting and pasting of polygons. So what do we mean if you're cutting and pasting polygons? So you start with a polygon. So we already have here a polygon. And the first thing you do is you cut it. So you can cut into different pieces. You can cut into all these sub-polygons. And what's the next part of the operation? Well, you take your sub-polygons, you're going to rearrange them, and then you can paste them back along the boundaries. So of course, there's a little bit of a rule that you're not going to take your pieces and overlap them. You're going to be pasting them along the boundaries. So now this P polygon over here, that P, and the Q polygon, they are what you call scissor congruent or cut and paste equivalent. A little bit more formally, so we can, how do we define this? We define a polygon P which is cut into different pieces, so as the union of a bunch of polygons, Pi. And then you also have another polygon, which is also cut into different pieces. Well, you say that they're scissor congruent if all of the pieces are isomorphic and the subpolygons only just interact at the faces. So that's what I was saying. There's a rule that you're not going to take a subpolygon and overlap it with another polygon. You're only gluing along the boundaries, along the faces. Okay, so this is the warm-up. As I said, this, of course, that was a very classical problem, going back to the Greeks essentially. But it did have a very important, it has a historical importance because this became, trying to generalize that idea of cutting and pasting of polygons, try to generalize that into higher dimensions, was essentially Hilbert's third problem. So that question essentially was, how about dimension 3? What happened? So this Hilbert gave this problem, dimension 3, to a student of his, Dean, and he thought, well, this is going to be a PhD problem, very hard problem. And if essentially Dean figured this out, it is a hard problem, but he figured it out pretty soon. And the question was, well, if I have just polygons, I know that the area is just going to be the only cut and paste invariant. But if I have polyhedra, is volume the only cut and paste invariant? Well, the answer is no. You could have two polyhedra, like the tetrahedron right here, and the cube, and you could have these two polyhedra, you could make them have the same volume, but even so, there's no way you can cut, for example, the cube, cut it up into little sub polyhedra and try to glue them. You're not going to be able to achieve the tetrahedron. So these two shapes, this tetrahedron and this cube, are not cut and paste invariant. So that was the essential contribution of Dehn with the Dehn invariant. He figured out an invariant that detects that the cube and the tetrahedron do not have the same. They don't give you the same result when you evaluate it on that invariant, and therefore they're not cut and paste invariant. The cube has then invariant 0, and the tetrahedron, well, it's non-zero. Right, so that was Dehn's contribution. The answer is no. Volume is not the only cut and paste invariant. You also have to deal with the Dehn invariant. And later on in the 60s, Snyder, I think, showed that volume and the Dehn invariant are the only cut and paste invariants. The story went on to 4 dimensions. What can you say about 4 dimensions? And Jensen proved that 4-dimensional volume and a generalization of the Dehn invariant are the only invariants that need to match in order to say if 2 4-dimensional shapes are going to be cut and paste invariant or not. And if you go on in dimensions, the problem gets harder and harder and harder. And in dimension 5 and greater than 5, it's still an open problem. So, you know, this, of course, gives us a little bit of the flavor that this is as you go higher in dimensions and you are try to go deeper into the problem, it becomes difficult. And of course, you want to have mathematical tools to deal with that. And one of the modern approaches to this notion of scissor congruence is via K-theory. And that's an approach that Ina Zakarevich and Jonathan Campbell have taken and applied to this problem and also to the problem of understanding varieties. So, you know, cut and paste problems need a lot of a good framework to understand that. And of course, K-theory, morally, philosophically, that's a good approach, because K-theory, at this K-note, a little bit tells you a little bit, you know, it's a divide and conquer approach. You can, just like K-theory allows you to express modules in terms of submodules. Well, that philosophy kind of gives you an idea of why K-theory could be a powerful tool to approach this problem. And as I said, it's a problem that appears in many contexts. You know, in the geometric world with varieties, in the case here with polygons and polytopes. It also has an importance in the world of manifolds. Yes, man. Yes, exactly. Yeah. Yeah. Okay. So yes, as we even saw it in Ernesto's talk like a minute ago, you know, these basic properties of the stringy spectrum. There was a notion of scissor congruence as well. Okay, so the problem that we were working with was specifically thinking about manifolds. So let me move on to manifolds and give you an idea of what do we mean by a cut and paste operation on manifolds. So let's start looking at the right-hand side here of the slide. So what you see there is we start with a manifold M, a closed manifold, and this is the very classical definition of a cut and paste property on, you know, operation on a manifold. We start with a closed manifold, and then we cut along a k-dimension 1 smooth submanifold with trivial normal bundle. The point of that is that later on we're going to want to paste along those boundaries. So, you know, you do want to be able to paste via some diffeomorphism, and you want to be able to do that smoothly and everything. So that's why you need a trivial normal bundle. Right, so choose your manifold, choose a k-dimension 1 submanifold with trivial normal bundle, do the cutting, and then glue back. You're going to glue back those boundaries via some diffeomorphism here. And what we say is that the original manifold that you started with and the new manifold that you've achieved after cutting and pasting are going to be called cut and paste equivalent. Cut and paste or scissors congruence, same thing, slightly different terminology. People got used to talking about in the world of manifolds about cutting and pasting more than scissors congruences, but it is exact same thing. Okay, so this is what we mean by cut and pasting of manifolds. Right, so as already mentioned, there was a group of authors, Craig among them, who defines the notion of classical schneiden und kleben groups, the cut and paste groups. So SK is for schneiden und kleben. It's the German terminology because this group of authors were German. And what was the definition of the group? So we start with a monoid. So the monoid of diffeomorphism classes of smooth, closed, oriented, n-dimensional manifolds under this joint union. And what you do is you take the Grothendieck group of that monoid and you quotient by a certain relation. What relation? Well, the relation is exactly the cut and paste relation that I was explaining a moment ago. So what you see here is two pieces. This is one manifold with boundary. This is another manifold with a diffeomorphic boundary. The little bar over there is for opposite orientation, so that you can, have this is, we're working with oriented manifolds, so maybe we're going to keep track of the orientations. And the two diffeomorphisms that appear here on the slide, this phi and the psi, they're both orientation preserving diffeomorphisms of the boundaries of the two pieces. M1 and M2 have the same boundary, and you're gluing along that boundary with an orientation preserving diffeomorphism. So you have these two manifolds, and those should be cut and paste equivalent. You're putting them in the same class in your group. Right, so this is the definition of the SK group. This is the classical definition of the SK group. Before we move on to seeing anything else, let's see a little bit of an explicit example of this cut and paste operation. So in this example, I'm going to start with a torus, with a two torus, and I'm going to cut that torus into a bunch of pieces. So I'm going to cut it into 4 different pieces. Now, just as I did with the little polygon and the polygon cat, I'm going to do the exact same thing here. I'm going to take those pieces, I'm going to rearrange them, and then I'm going to be gluing along the boundaries, just following what the definition of the group was. So what you see here is that I'm starting with the torus, two torus, and the result after this operation of cutting and pasting happens to be the disjoint union of two tori, so two tori. Well, that has an important implication, because the implication is that I have a torus, and then that the class of one torus is going to be in the SK group is the same class as the class of two tori. But how is something going to be equal to twice itself? The only way that can happen is if it's actually representing 0. So that means that a torus will represent 0 in the group of cut and paste group of manifolds. This example is showing dimension 2. This, of course, also generalizes for higher dimensions. So this could have been the picture of a mapping torus, a higher dimensional mapping torus, where you have like you have a manifold, you cross with I, and you glue your two ends together via any diffeomorphism that you want. You get a mapping torus. The same procedure of cutting into pieces and then getting two copies will still hold. So this example generalizes for mapping tori, and in general, we know that for any dimension that you want, mapping tori, any dimension of mapping tori is going to be 0 in whatever dimension you've chosen in cut and paste. So mapping tori are 0, which is not true for cobordism, as we will see. Okay, so how about cut and paste invariants in this classical setting? So the Euler characteristic is one of our cut and paste invariants. The signature of a manifold is also a cut and paste invariant. So the signature of the glued manifold can be decomposed into the sum of the signatures of the pieces. And because the theorem of Novikov additivity, we know that this is going to be just the sum independently of whatever gluing map you decided to have there. That doesn't affect the result of the computation of the signature. So these two are cut and paste invariants, Euler characteristic and signature. It turns out that those two and linear combinations of them are the only cut and paste invariants for manifolds. Okay, so these are the invariants. Now, as I already said, to give you a little bit of the flavor of what's coming, is that formalizing the notion of scissors congruences and cut and paste invariants via K-theory gives you a powerful tool to understand this problem. And I already mentioned Campbell and Zakharevich, how they have worked and have like a lot of work done with scissors congruences of polytopes as K-theory spectra. So in our work, we wanted to kind of translate a little bit and see what we could get out in the world of manifolds by using those same ideas. Now, direct applications of the ideas were not so easy. So when we first started our project, we said, okay, so this is probably, are we going to be able to write a manifold where they just write variety, or it doesn't work exactly like that. So the problem, what is the one essential problem that we found almost immediately was that if you have a polygon or just a polytope and you cut it into different pieces, well, you are getting the pieces when you cut are still objects, or are still the objects of the same nature of the original thing you started with. So you start with a polytope and you cut it into pieces, well, you are getting little polytopes. So the result is something of the same nature as the big thing. With manifolds, in the classical theory, we saw how we started with closed manifolds. When you take a closed manifold, you cut it into pieces, and now the resulting pieces are also manifolds, but they are manifolds with boundary. So you have these things have boundary here, and now we see that there's like, even philosophically, you see there's already a difference between the situation with polytopes and the situation with manifolds. The pieces over there were things of the same nature as the big thing, but the little manifolds that you have achieved there, I mean, they have a difference. They are manifolds with boundary versus the closed manifold that we have here. So that's an essential difference between the two stories. Now, what can we do? Well, we decided to generalize in a certain direction, and instead of like working with the classical SK groups for closed manifolds, we decided to generalize the groups to be groups of manifolds with boundary. So this slide looks like suspiciously similar to a slide we saw before. This only just highlighted like a few differences. And the first difference you see up here is that instead of starting with the monoid of closed manifolds, blah, 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 with all of the conditions, we are going to start with a monoid of diffeomorphism classes of smooth-oriented n-dimensional manifolds with boundary, and again under disjoint union. So now we're working with manifolds with boundary. Take the just as before, take the Grothendieck group of that monoid and quotient by a relation. And the relation here also looks similar to what we had before. You have your pieces. You're going to be gluing via some diffeomorphisms. But now your diffeomorphisms are not gluing along the whole boundary. Your diffeomorphisms phi and psi over here are orientation preserving diffeomorphisms of just submanifolds in your boundary. So maybe you're not going to be gluing along the whole boundary. You're going to be gluing along some submanifolds. And that is, well, that's all fine, but we did have some rules on how you cut and what you're allowed to paste. So the next slide gives you an idea of what those rules are. So what's the key idea? So the key idea here is that you have a manifold with boundary, and you're going to do a cut and paste operation on it. So that boundary, the already existing boundary, you're not going to touch. Okay, so if I'm starting with this manifold on the right, suppose it's already glued over here. So I'm starting with this manifold on the right, and I want to perform a cut and paste operation on it. I'm going to be leaving this pre-existing boundary, this one too, this boundary was pre-existing. So all of those pre-existing boundary components, I'm not going to touch at all. So you're going to do the cutting in some other part of the manifold. And then when you do the gluing, you're going to be gluing along the boundaries that you've created. You're not going to be touching the already pre-existing boundaries right there. So that's an important rule, that if you're cutting and paste, you're doing your cut and paste operation on a manifold with boundary, you do not touch the boundaries that were already there. The pre-existing boundaries, you just leave them. Okay, so good. So doing, now we've done giving you the definition of what our SK boundary group is. In our first collaboration paper, we determined a short exact sequence which relates our new group here, the SK boundary group, and the classical SK group. So the classical cut and paste group and the one that we had with boundaries. So as you would expect, you can always have this one. So okay, so if you have any class of manifolds in here, they're going to be closed manifolds. Well, that's going to be sent to its own class in manifolds with boundary. It just happens to be manifold with boundary where the boundary is empty. That can happen. That's allowed. And what happens under the next map? Under the next map, you're going to have some class of manifolds. Now that n does have a boundary. And what the next map in the exact sequence does is it just sees the boundary. So what is that C n-1 over there? Well, if I'm taking that boundary map, I'm definitely landing in manifolds that are one dimension less, because the boundary is going to have one dimension less than the big manifold. So that's why we're getting like n-1. And what is it? Well, it's a Grothendieck group of a monoid of diffeomorphism classes of n-1 dimensional manifolds that bound. And that bound is because, well, you're expecting these guys to be the boundaries of manifolds that came from here. So those manifolds bound, and you're just taking that Grothendieck group. It's a free group. So that exact sequence actually splits, which is nice. Okay, so that's that we are relating there the classical version with the our cut and paste group with boundary. Okay, so now moving on with like trying to formalize this via K-theory. As I said, the many already existing papers of Campbell and Zakharevich, they didn't have quite the framework that would work for manifolds. They did have some very interesting work in progress, which they were very, very generous to share with us. And this was an interesting categorical concept, which was the notion of categories with squares. So I'm going to walk you through now, like the next few slides are going to be reflecting a little bit the work that Campbell and Zakharevich shared with us about what are categories with squares. And then after we see this in generality, I'm going to say how we apply this to the world of manifolds. Right, so what's the definition? What's a category with squares? So a category with squares is a category. We are going to have a base point object. And the category is going to have, as all categories, is going to have morphisms, but we're going to have morphisms in two subcategories of morphisms, cofibrations and K-fiber maps. And maybe the most important piece of information in this slide is that the category comes with distinguished squares. Now, distinguished squares are part of the data of your category, so you can choose what you mean by those squares. if this is general theory, then you will, in certain applications, you would have to choose what you mean by the squares. And the distinguished squares mean that you have chosen what squares you allow your category to have, what is going to be part of the data. So distinguished squares are an important feature of this category. Now, of course, these are some conditions. What are the conditions here? So the category has co-products and distinguished squares, and those are closed under, those are closed under co-products. The distinguished squares are commutative, and you can stack them. You can compose them both horizontally, and you can also stack them vertically, and you have this notion of composition. Both the co-fibrations and the co-fiber maps, which remember was the two types of morphisms that you have, they all contain isomorphisms in the category. And finally, another important feature or condition of these categories is that those two little squares that you see at the bottom of the slide, and that if you allow equality here and an equality here, these two, or vertically as well, these are going to count as distinguished squares. Right, so this is a very interesting categorical framework that actually connects with the notion of Waldhausen categories. So if you have a Waldhausen category, if I give you a Waldhausen category, then we can give you a category with squares. So the horizontal maps are going to be the co-fibrations in the Waldhausen category. The vertical maps are allowed to be all maps, maybe not just co-fiber maps, but all maps. And of course, the distinguished squares have the property that if you take the push out, including B and C via A, that's going to be weak equivalent to D. So there's this connection with Waldhausen categories. Once you start thinking about K-theory spectra, this equivalence is this connection is very important. Right. So so now we move on to K-theory spectra. What do we mean by K-theory of this category or squares, category with squares, with distinguished squares? So what you mean is that you have that bisimplicial set. You take the geometric realization, and you also take base loops, and that's what your K-theory is. In fact, you can show that that's an infinite loop space. And this is done in quite a bit of detail in our first paper, is that there exists an equivalence of K-theory spectra of the squares K-theory of the category with distinguished squares. You can show that that's equivalent to the K-theory of your Waldhausen category. Okay, so this is the framework. Now, what about that's the framework? That's the spectrum. What about pi naught of that spectrum? So, if you take pi naught of your K-theory spectrum with squares K-theory, what you're going to get is, well, K naught is going to be this free group on the objects in your category, and you're going to be quotiented by the equivalence relation that's given by these two features. You have your base point, and you also have this connection here, which has to do with whatever you have as your distinguished square. So for every distinguished square that you have in your category, you are going to be having this relation of like A plus D is going to be equal to B plus C. So that's like you have this cross diagonal relation for every distinguished square, and that's the relation that gives you K naught in this case. Again, this will feature later, and this will be very, very significant when we see the application for manifolds and for cutting and pasting. Okay, so now we are going to move on with manifolds, and we are going to try to see how to apply all of this categorical framework to the notion of manifolds. So what we are going to be defining in the next slide is this notion of a category with squares for manifolds with boundary. Right, so what are going to be my objects? So the objects are going to be smooth compact, and manifolds. Morphisms, in this case, are going to be smooth embeddings. And when, that should give you a little bit of pause. Smooth embeddings, what do we mean here? So the embeddings, of course, we are allowed to choose. So we are allowed to choose which morphisms we have in our category. And our choice here is that there's a rule that if you're trying to embed this manifold M in this manifold M, and of course, N and M have the same dimension. So what you're trying to do is where are your boundaries going to go? So the boundaries are either going to go, we have to like these boundaries, either going to go to either the interior, completely to the interior of the manifold, or onto the boundary components of M. So these two that I just highlighted, you see how they're going in here. And maybe this other boundary here is going completely to the interior. So we do have this rule, since we are allowed to choose, because we are essentially creating the data for our category. That's a choice on what our morphisms are going to be. And that's how you, that's when we mean smooth embeddings, that's exactly what we mean. And especially one has to be a little careful about where the boundaries go. And again, we also have a choice, we have a control on what we are going to allow our distinguished squares to be. And you see what we are seeing here is essentially just a push out of manifolds. So that's the general, this is the general statement. And over here on the other side, you see an example. So what do we have here? So essentially we have a push out of manifolds. So up there, we have a small manifold N, and that has this nice smooth embedding following the rules that I established up there. Also, this vertical map is another smooth embedding. And now, if we're taking the push out, where we're taking is, well, we're gluing those ends here. We're gluing this and this along the orange submanifold there. And this is the result. Now, it could be, it could be that, one thing that we worried about quite a lot was that, of course, manifolds and pushouts behave in a very evil way in general. If you're just taking pushouts of manifolds, in general, you could have, like, suppose you have a copy of R and you have another copy of R, and you're taking a pushout by, say, 0. Well, you're getting 2 lines. That's not a manifold. So in general, the category of manifolds behave like really, really badly with pushouts because the result could be that it's not a manifold. But that was the beauty of the distinguished squares. The distinguished squares allow you to choose, and they allow you to have as data in your category only things that you want. So you can discard any pushout that doesn't work because you can control what you mean by the distinguished squares, and you can just have the ones that give you the correct result. Okay, so this is how you use the framework of categories with squares with manifolds. Now, since you've now using just one example of the general category, you can follow through with all of the technology that you've had before with the K-theory spectrum and pi out of the spectrum, and so you can have that as an example. And interestingly, when you take the K-naught of K-theory over your specific example here, manifolds with boundary, what you get is the cut and paste group of manifolds with boundary that we define. Of course, the proof in the paper maybe takes a little longer, but I do want to give you an idea of why that should be the case. So we remember that K-naught was, well, just this K-naught was here. Remember that this is just the free group on objects. The objects are now manifold with boundary, quotiented by the relation of the squares, the 2 diagonal squares, A plus T equals B plus C. And I want to motivate a little bit why that would giving you the notion of cut and paste equivalence in the SK boundary group. So let's have a look at these 2 diagrams. So in these 2 diagrams, I mean, there seems to be like a lot of pictures, so let me walk you through that. So if you observe the two diagrams, the one on the left and the one on the right, you see that A is the same as A, C is the same as C, and B is the same as B. So D in the end ends up being different. Let's see why. So this vertical arrow from A to C, that's also the same in both situations. But one difference that you can note is that the way we are embedding our A into B is different this is a game of spot the difference. So you see that that's different there. So in the first one, the little green cube went into the first component, and the red went into the other component. And you see how psi is swapping the two components. So that's going to give me a different result when I glue. Okay, so you see, let's see. So we have the two different components. Now we are gluing. So here in the first one, I'm gluing this with this via the red. So that gives me this component, and the green via the green. So this gives me the other component. And what do I know? Well, I know that if I take this distinguished square later on in my K-naught group, that's going to establish the relation that A plus D is equal to B plus C. So I have this diagonal and the other diagonal. A plus D is equal to B plus C. So essentially I can rewrite that as D equals B plus C minus A. Okay, now what about the other square on the right? So now the pieces are the same. How does the gluing go? So the red is glued with the red, so I get this component, and the green is glued with the green, so I get this other component. So you see the resulting manifold is different, but still I can establish the same relation. A plus D prime equals B plus C prime. So D prime is, again, B plus C minus A. So in this group, D and D prime are the same. So that's exactly what establishes the cut and paste equivalence and the connection with K theory. Of course, the proof is a little longer. That's stuff for the paper. Okay, so that's the idea of the connection between K theory and SK of manifolds. So in our first collaboration, we also investigated lift of the Euler characteristic, and you can see that there's a map. Well, you know that map is not non-trivial, but you do have a map of K theory spectra from K theory of this category with squares of manifolds and K of C. If you take pi naught here, you take pi naught, and you take pi naught on this side. Well, what you're getting on this side is your pi naught of your K theory, but we've just seen how that's just a K boundary. And on this side, we get C, and this is detected by the Euler characteristic. That's not an isomorphism, but it does detect the Euler characteristic. So yeah, so as I said on the slide, on pi naught, the maps agree with the Euler characteristic for the smooth manifolds with boundary. Wait, okay, so now what about the connection with cobordism? So just a recap of what the cobordism relation is. So we have this notation for the cobordism group. You can think about n manifolds up to cobordism, and the connection is that you're going to say that in that group, two manifolds M and N are cobordant or belonging to the same class if there is an n plus one dimensional cobordism. This is n dimensional, and this will be n plus one dimensional. If there is an n plus one manifold that has both those things as boundary, then you're going to say they're in the same class in the group. So what's the connection with cutting and pasting? So it turns out that there's no map like this, and there's no map like that. So those two groups seem to not want to relate. There is something that you can do, is that you can construct a group which has both the relation of cutting and pasting and the relation of cobordism. So what you're going to get is this group, which is in the classical theory is called SK bar, and it's both a cobordism and a cut and paste group. It has both relations. And well, okay, so if I wanted to say, for example, I have two cut and paste equivalent manifolds, and I want to construct a cobordism between them, what is going to happen? So you see on here, on this side, I have my two pieces, M and N, and on this side as well. And of course, this N and M prime are cut and paste equivalent. Now, what I'm going to do, I want to try to construct a cobordism between them and see what happens. So I've taken my piece, submanifold with boundary M1, and taken it cross the interval, and also cross the interval here. And then you have these two, well, M1 cross I and M2 cross I. Now you have these boundaries, and you're going to start gluing. Maybe like 1/3 of the way you're going to glue via phi, and 1/3 of the way you're going to glue via psi. And in the middle, what are you going to get in the middle? So in the middle, you get a new boundary component, which looks like this. And this looks exactly like a twisted double, or equivalently like a mapping torus. So the slogan here is that SK equivalent manifolds, like what you have here and here, SK equivalent manifolds are going to differ in cobordism. So if you construct a cobordism between them, they're going to differ by a mapping torus. Okay, that's classical theory, and that allows you to construct this short exact sequence. This is again from the Karras, Craig, Neumann, and Osa book, very classical book. They have this nice short exact sequence where you have that, you know, if you're looking at cobordisms and you have this surjection onto the cut and paste cobordism group, well, what are you going to be seeing as the kernel of that? Well, as that kernel is everything that, well, things that could be non-trivial in cobordism, but that are trivial when you quotient by the cut and paste relation as well. And what did we see at the beginning? We saw that the example with the torus came to be 0 in SK. This mapping tori tends to be 0. So, you know, you do see the motivation for this exact sequence here. Mapping tori 0 in cut and paste. The vertical exact sequence is an analog for what happens if you're going from SK to SK bar. So, well, what you're going to be seeing here are things that maybe are not 0 on the cut and paste, which is things that are generated by spheres. So those spheres are 0 in cobordism. So once you quotient by the cobordism relation, those spheres are going to vanish. And over here in blue, I've already written down a little bit of a description of the group. So the first kernel here is going to be 0 when n is odd. It's going to be generated by spheres when n is even. You're going to have this Euler characteristic and the signature, as I said, were invariants of this SK group. The only remaining invariant here is the signature. And okay, so we have already said about this mapping torus. Now the bordism, of course, bordism is a very rich group, has lots of invariants, Euler characteristic modulo 2, the signature, and of course other Stiefel-Winnian and Pointryagin numbers. But once you look at like converging to the cut and paste cobordism group, this SK bar group, the only remaining thing is the signature. Okay, so that's classical theory. Now remember that we were working with cut and paste group of manifolds with boundary. So somehow we actually want to be able to generalize those things to our context. So we already had this context of manifolds with boundary. Let's see how we can generalize that. We know what we've already seen how to define this cut and paste boundary group. Now, what about the cut and paste cobordism group, SK bar group? Well, let's see. You have to be a little careful on how you define things, because in general, cobordism groups of manifolds in boundary with boundary in general are 0, and you don't want to end up having a trivial theory. Why is that true? Why is that the case? Well, in general, if you have a cobordism, you have manifolds with boundary, and you try to construct a cobordism between them, and you allow any boundaries whatsoever, well, then you could have, suppose you're trying to do a cobordism between this manifold M, and this manifold M prime. So you're trying to do that cobordism, and you allow anything. Well, you could just take M cross I, and M cross I, you have here boundaries which are allowed, and so that means that there's no restriction. You could have any manifold M and any manifold M prime, and you could just construct a cobordism between them. So that means that everything is going to be, the zero class. So that's a problem, and we needed a way to come around that problem. If you establish some conditions or restrict conditions on what you're allowing as a boundary, then you do end up with situations where you have like non-trivial theories. So in our framework, we decided to work with what we called trivial boundary cobordism. And what is this? Well, the picture is already very suggestive. So we are constructing a cobordism between this manifold M, which is boundary, and another manifold M. And then what you're allowing with this extra boundary that you create when you are constructing the cobordism is just the boundary of M cross I. So that additional boundary component is just a tube, it's just trivial. Okay, so that's what we called trivial boundary cobordism. Now, you can construct a monoid of n manifolds with boundary up to trivial boundary cobordism, and you can take the Grothendieck group of that. And well, okay, so in the second part of this project that was with Renee Hoekzema and Semikina, we constructed this exact sequence which relates the classical cobordism group with our cobordism group with trivial bordism. This Cn we've already met. This is just the when you take the boundaries, just as the Grothendieck group of diffeomorphism classes of null bordant manifolds. But interestingly, we do have a kernel here because, well, mapping tori happen to be trivial in trivial boundary cobordism. Why is that? This this picture is explanatory of why that would happen. If you have M, you have this. In this example, it's a twisted double, M and N, and you have like over here you have M and again M. Well, then you're going to get this relation, and that means that this twisted doubles are always cobordant to mapping tori. So in this context, it really doesn't matter so much if I'm saying twisted double or mapping torus. So this is going to be zero in the trivial cobordism group. So you do have this kernel happening in this exact sequence. Okay, so that's a four sequence. That's a four-term exact sequence. And we're going to use that four-term exact sequence to now see what's the connection between trivial boundary cobordism, the group, and SK bar. And turns out that I could have just taken my four-term exact sequence here. I can take this, quotient here so that I get a short exact sequence. So it's just a rewrite. And now we see, what do we see here? So we had, well, I explained before the existence of this short exact sequence, which related the classical SK groups with the SK boundary groups. Of course, there is an analog in the SK bar situation, which can be shown in a very similar way. Now, how does that relate with the four-term exact sequence that I just showed you? So if you take this last term, it's going to be the same term, the same group, and it's free, so this sequence is split. Now I have my exact sequence down here. I also have the consequence from the sequence in the slide up here, and now I can see that I can construct these isomorphisms. The first isomorphism here is classical, so this is classical theory. So that's a classical group. That one, they was just saying that if you water classes in cobordism that are going to disappear when you take cut and paste relations, well, those are the things that disappear are the mapping tori. So that one is classical. The other groups are the same groups. Therefore, the thing in the middle has to be an isomorphism. So there is an isomorphism between these two groups here. And finally, just to wrap up, we're getting closer to the end. We actually, as we saw, we can categorify our cut and paste group with boundary in these squares of manifolds. Can we do a similar thing for SK bar boundaries? So can we categorify the cobordism cut and paste group of manifold with boundary? So the answer is yes, you can. I will explain in a moment a little bit of how that big cube over there works. But it was interesting for us to note that the categorical framework of Camper and Zakharevich, where they work with these categories with distinguished squares, there's no reason where you would need to just say squares. You could actually have cubes, or even like n-dimensional generalization of n-dimensional cubes, where you can have like more data. Is absolutely possible and fits very well into that framework. And that is what we were using in here. So instead of like looking at distinguished squares, we're now looking at distinguished cubes. Now let's have a look at that cube. So that cube has the front face of the cube is going to be exactly the same as the cut and paste squares. So you have your SK embeddings of manifolds, just as you see here on the left, both vertically and horizontally. Now, in the third direction, in order to get where we wanted, we used a different type of morphism, which is the trivial boundary cobordism. So if you were to draw this with manifolds, it could give you a very complicated picture. But what you're seeing here is A is a manifold, B is a manifold, this is an SK embedding. But if you look from A to A prime, that is going to be a cobordism. Now, A and A prime have a manifolds with boundary. They have the same boundary components. So that's what you see here in the pictures. This is your A, and this back here is your A prime. So sitting there is your cobordism W naught. Now you can drag along and go to the other side, B and B prime, B and B prime. And you can have that, of course. You need some coherence relations here in your cube. So if you're doing embeddings in the front, embeddings in the back, that doesn't automatically mean that you're going to be able to embed your cobordism into the other cobordism, but we do want that. So there's also this part of the data in the cobordism group where you're going to embed the whole cobordism onto the cobordism. So this cobordism in this arrow, you want to be able to embed into there. So you do need this big F in the embedding one cobordism into the other. And that's again, like you could say, well, that's a lot of data. Is it going to work? Well, yes, it's going to work because this is a distinguished cube. It's a choice that you've made on what's the data of your category. So since it's a distinguished cube, and if you get a cube that doesn't work, you just throw it out. You don't let it be part of the game. So distinguished cubes again allow you to control the data and work with what you want. So what happened here? So just to recap what we did in the first part of this story is that we had our distinguished squares with manifolds. We were able to define the squares case theory by taking the geometric realization and loops. And then I already explained how taking pi naught of the spectrum coincided with the SK boundary cobordism. And then I was just talking about the cubes. What happened in the story with the cubes? Well, we did topologize the cubes, and what we had was now a trisimplicial space, because now you have three directions. You have a trisimplicial space. You take the fat geometric realization of that, take loops, and you end up with an analog. Here was K theory of squares. Over there you have K theory of cubes, and well, maybe part of the hard work in our paper was maybe that this showing that you do have that isomorphism with the cut and paste cobordism group of manifolds with boundary. Okay, so essentially that's all I wanted to say. If you want to see more details, there's 2 papers out in the archive. And I think that Julia and Mona and Josh Rapsis are working on Pi1 of the spectrum. It's probably going to be out soon. And then another part of this big team, we're working on lifting the signature, also on equivariant versions of these groups. So there's some work in progress as well. Okay, so thank you very much for your attention.